Good afternoon, dear listeners, and welcome to today's class. Today, in our class, we will be looking together with you the concept called conditional probability. Conditional probability. Conditional probability. What do we mean by conditional probability? Conditional probability is the probability of an event happening based on condition. And of course, this condition is nothing but the fact that another event related to this event earlier had happened. For instance, consider the probability of event A occurring based on the information that event B, which is related to this event A, already had happened. That is what we call conditional probability. Some real life explanations or concrete explanations of conditional probability can be seen in the following illustrations that I am about to give. Let us consider, for instance, that a little child goes out playing every evening. And the probability that this child goes out playing every evening is 0.75. Therefore, in any particular selected day, the probability that this child has going out to play is 0.75. But then on a particular day, the day has turned out to be rainy. So the question becomes, what becomes the probability of this child going out to play on that particular day, given that the day has turned out to be rainy? The first probability of 0.5, which the child has going out every evening to play, is an ordinary probability. But the probability of the child going to go out to play on that particular day selected, given that that day has turned out rainy, is what we call conditional probability. Because the probability of the child going to go out to play will be dependent on the probability that's a rainy day, or that depends on the probability that the day had turned out rainy. One illustration. Another illustration could be, for instance, in a particular locality, it is known that the probability of rain going to fall in that locality is 0.35. Therefore, in any random selected day, the probability that it rains on that day is 0.35. However, on this particular day that has been selected, we also have information that that day is cloudy. And we are now saying, what becomes the probability of rain going to fall on that particular day, given that that day is already cloudy? This is a conditional probability. So, based on these illustrations, we can clearly see that oftentimes that the probability of events occurring can be altered by the fact that an event that is associated to it already had occurred. These are what we call conditional probability. Having understood what is called a conditional probability, how do we now represent this conditional probability such that when it is seen, it is understood that they stand for conditional probability? For us to represent it, we are going to use events A and B to showcase it. events A and B. Event A and B. And in these events A and B, we will be talking on the probability of event A occurring given that event B already had occurred. Is a conditional probability. How do we represent it? It is represented as probability of A given B. So any day you see an expression like this, it stands for a conditional probability. Probability of A occurring given that B earlier had occurred. Or it can be represented this way, probability of what? A given B. This and this mean the same thing in mathematics and probability. Both stand for conditional probability of event A occurring given that event B already had occurred. Or it can equally be represented as probability of what? A occurring given that B earlier had occurred. So this and this and this mean the same. They all stand for conditional probability. However, when our emphasis is on the probability of B given that A earlier had occurred, of course, these expressions will be rewritten in this way. Then we have probability of what? B given that A had occurred, or we have probability of what? B given that A had occurred, or probability of what? B given that A had occurred. These are probabilities, the way we can express conditional probabilities of event A happening given that event B had happened. And this is the way we can represent the conditional probability of event B happening given that event A earlier had happened. This is how to denote or to present a conditional probability. Having understood the conditional probability, having understood how to denote the conditional probability, how do we express conditional probability? For the expression of conditional probability, I am going to give it in form of what? Of definition. And then from the definition now, we can then derive the formula of the conditional probability without confusing our listeners. Of course, conditional probability is defined as the ratio of the probability of the intersection of the events to the probability of the event that earlier happened. I repeat, the probability of the intersection of the events to the ratio or the ratio of the probability of the intersection of the events happening to the probability of the event that happened earlier. That is how to define a conditional probability. Ratio of the probability of the intersection of the events to the probability of the event that happened earlier. That is the definition of a conditional probability. So I'm going to define it on the board and then we'll make some derivations. Okay? So permit me to clean this. So we are saying that conditional probability is defined as this is equals probability of the intersection of the events, probability of the intersection of the events all over probability of the events that happened earlier. This is the definition of conditional probability. Here, this thing stands for happened, for me to manage the size of this board. We earlier had established that the conditional probability is denoted by probability of what? A given B. That is how we denoted it. Based on this definition, of course, it is now going to be that this is equals probability of A intersection what? B all over probability of event that happened earlier. Based on this denotation, this B happened earlier. So it is going to be all over probability of what? B. However, when we have probability of what? B given what? A, it is going to be still probability of A intersection what? B all over probability of the one that happened earlier, which is what? A. Probability of what? Of A. So this is the conditional probability of A given B expressed this way. Conditional probability of B given A expressed this way. Therefore, to solve conditional probability, what we require is to know the probability of their intersection and the probability of that event that happened earlier. The moment we know these two things, definitely we can find what the conditional probability. How do we do this illustration of what we have done with either a set or anything simpler? Based on this definition, we arrive at this formula. And based on this definition, we arrive at this formula without confusing anybody. So this is a conditional probability, this is a conditional probability. So permit me to clear here why we use a set to showcase more what we mean by this conditional probability formula. So permit me to clear here. Let us still make use of events A and B, okay? Then using what we call a Venn diagram, where the Venn diagram represents the sample size or the sample space. So I have a Venn diagram this way. I have a Venn diagram this way, okay? Then I have a set, and I equally have another set. This is my set A, this is my set B. This is set A, this is set B. This center here, of course, is the intersection of set AB. So here is A intersection B. That is this particular place. A intersection B. Of course, here is what we call, let me write with what S. This thing stands for what? As a sample space. Everything that is contained in the model set. So given this illustration now, if I am talking about the probability of A occurring, given that B earlier had occurred, it is going to be probability of what? The intersection of A and B to the probability of what? The B that earlier occurred. And of course, when you come to this intersection here, we'll be talking about the number of elements that are inside A intersection B. So if I want to solve it using that set approach, I am going to come and I will say, illustrations, we have what we call N of what? S. When we write n of S, we are talking about the cardinality of the sample space, the number of elements in the sample space. That's what we mean by this. So we now write n of what? Of A. When we write n of A, what we are talking about the number of elements inside what? A. We talk about n of what? B. When we talk about n of B, we are talking about number of elements in what? In B. And when we talk about what? N of what? A intersection what? B. We are talking about number of elements inside the A intersection what? B. Now, for me to be able to find the probability of this n of A or the probability of event A, it is going to be the number of elements in A all over the number in the sample space. Which means I will say that my P of A is given as what? N of what? A all over what? N of what? S. Number of elements in the sample space all over number of elements, number of elements in event A, then all over number of elements in the sample space. That is the probability of what? Of A. Then probability of B is going to be N of what? B all over what? N of what? S. And then my probability of what? A intersection B is given as what? N of what? A intersection what? B all over what? N of what? S. Okay? This is now the probability of event A, probability of event B, probability of event A intersection what? B. And we are saying that the conditional probability is the ratio of the probability of the intersection to the event that occurred earlier. So if I say P, therefore, P of A given B is talking about the probability of event A given that B had occurred. I'll ask myself, this thing is expressed as the ratio of the probability of the intersection. And look at the probability of the intersection, which means I have what? N of what? A intersection what? B all over what? N of S. N of what? S. This sign here is what I have written here. That is P of A intersection what? B. And we are saying that this is the ratio of the number of elements, the probability of the number of elements in the intersection to the probability of the event that happened earlier. Which event happened earlier? This is what B. So I will now say divide by, I am talking about probability of B. Look at the probability of B. N of B all over N of S. N of what? B all over what? N of what? S. This equals. Of course, the whole of this quantity is P of A intersection B. So I have P of A intersection B all over, because the division sign is all over. Here is N of B all over N of S. What is N all over B, which is P of what? B. So all over what? P of what? Of B. So when they give us problems related to sets, and they still ask us questions on conditional probabilities from it, what is required for us is to diligently obtain the probability of the different events and obtain the probability of their intersection. The moment you do so, you can go a long way to solving that particular problem. That is what we mean by conditional probability. The next question here becomes, there are what we call properties of conditional probability, which we want to prove. Some might call it the axioms of a conditional probability. So I'm going to clean this. We now go into the axioms or the properties of what? Conditional probability, and see whether we can prove them together and be able to have a complete understanding of conditional probability. So permit me to clean here. The number one property of a conditional probability, properties. Or let me use the word, yes, of conditional. Let me use the word property of conditional probability. Please permit me to write this way. I'm referring to this as a conditional probability. Number one, they say the probability of A given B is always greater than or equal to what? 0. Or probability of B given what? A is always greater than or equal to what? 0. This is also a property of even the probability on its own. That is number one property. Number two property, they say, number two, the probability of S given A equals what? 1. And the probability of A given A is equals 1. So how do we show that the probability of sample space given that event A, which is of course associated with the sample space, is 1? Probability that sample space occurs given that event A associated with that sample space earlier had occurred. They told us it is what? 1. How do we show it? And the probability of event A happening, given that same event A earlier had happened, they told us that it is what? It is 1. How do we show this? We go about showing it this way. We say, we are going to express this as a conditional probability we know. So we now write proof. We want to prove it. So we now say P of S given A is given as P of what? S intersection what? A all over P of what? A. This is based on the expression of a conditional probability. That probability of S given A is expressed this way. And we are talking about a sample space and talking about event A that is contained in the sample space. If you have a sample space and you have another event which is contained in that sample space, it means that what that sample space and that event have in common is the same thing as that event. For instance, you are saying that your sample space S is given as 1, 2, 3, and 4. And you are saying that you have event A, and that event A is 3 and what? 4. And you want to find the intersection between this S and this A. You find out that S intersection what? A is given as, what is it that are found in sample space which are equally found in what? In A. 1 is not here, 2 is not, 3 is here, so I will take 3. 4 is here, and I will take 4. And of course, you know that this 3 and 4 is equal to what? A. So it means that my S intersection what? A is equal to what? A. In as much as the intersection here is 3 and 4, and 3 and 4 is equal to what? A here. So sample space intersection, any set that is associated with that sample space is the same thing as that set. Okay? So if you agree with me with this illustration here, I will come here and say, therefore, this thing becomes probability. In place of this S intersection A, I have proven that S intersection A is what? Is A. So in place of this, I will now write probability of what? Of A, which is now this, all over probability of what? A, which is the denominator. This is the denominator, this is the numerator. So probability of A cancel itself 1. Probability of this A cancel itself is what? 1. 1 divided by 1 is what? Is 1. So the probability of sample space given that a set A that is associated to that sample space earlier had occurred is equal to 1. How now do we show this one equally? It is still almost very same thing with this one. But let us equally clean and show you. What we did here was to write the probability of a S giving A the way we know the expression of a conditional probability. The moment we have written it down, we recall to ourselves that that the sample space intersection event A, which is contained in that sample space, is the same thing as event A. We showed it here using numbers. And if you agree with me, we are going to remove S intersection A and replace with A in as much as they mean the same thing. And that's what I did here. In place of S intersection A, I wrote A all over P of A, which is what I had earlier. And this will cancel this to return what? 1. So this is how this one was proven. Permit me to clear here while we show this one. Okay. Now the second one says that P of A given A is given as P of A intersection A all over P of A. This is just like expressing it the way we know as a conditional probability. So, but the moment we express it this way, we recall to ourselves that you know that A intersection A is A. If you have a set A, 1, 2, 3, 4, that set A, 1, 2, 3, 4, you ask yourself, what do they share in common? Of course, it is what? That A that they share in common because it is 1, 2, 3, 4. Because what you are trying to say, that you have a set A, that set A is 1, 2, for instance, that set A equally still remains 1, 2. So you ask yourself, what is it that they have what in common here? Which is talking about what? A intersection what? A. 1 is here, 1 is here, they have it in common. 2 is here, 2 is here, they have it in common. Which means A intersection A is A. So if A intersection A is A, it means I am going to use A in place of A intersection A here. So this thing becomes P of what? A all over P of what? A. And of course, this is 1 and this is 1. And this gives me 1. So the conditional probability of any event given itself is 1. Note it. Probability of any event given itself is 1. Probability of sample space given any event found in that sample space is what? Is 1. Very important. So I want you to note these key two things for me. So this is the first, we have written this one. This is the second, we have shown this one, we have shown this one. I don't want you to forget this for me. So we now move over to the third property of the conditional probability and see whether we'll be able to show it. So permit me to clean here while we go back to that. Okay, the number 3 property says, which we are going to write and prove. The number 3 property says, and I write, Number 3 says that let S be the sample space of an experiment and A and B be any two events. Let E be any other event such that P of E is not equal to 0. Then P of A union B giving E equals P of A giving E plus P of B giving E minus P of A intersection B intersection C giving E. That's what they want us to show. That thing I wrote on the board is true. So we are going to take our time and try to see whether we can show this thing clearly. Okay? So what we are equally going to do as usual is we are going to express this one as the normal conditional probability that we know. This very one. Expressing this one as the normal conditional probability we know, so we are going to write proof. We want to show it. We write proof. And that proof becomes that my P of A union B giving E is equals P of A union B intersection E all over P of E. I have just expressed this thing as the conditional probability we know. Just like we have a conditional probability of a P of A giving B. You express as P of A intersection. But what we have here is P of A union B giving E. So it becomes P of A union B intersection what? E. All over P of what? Of E. Okay? Then we are going to use what we call property of sets. Property of what? Sets. And that property of sets says that any day you have probability of A union B intersection E, that it can be written as that this equals probability of this A here intersection E close it union. What you have here is B, so you have probability of what? B intersection E, you close it, then all over. You have what we call P of what? E. That this can be expressed like this. At this point in time, we are equally going to call on another property which we call it addition law of probability. Addition law of probability. And I will recall for you what we mean by addition law of probability. That whenever you have what? P of A union B, that it is P of A plus P of B minus P of A intersection B. Okay, as long as this A intersection B is not empty set. If it's an empty set, it will end this way. So I'm going to express this the way I express this thing here. I am seeing this A here as if to say it is A intersection this. Okay? So that is the manner I am going to express this. And expressing it that way, I am going to say that this thing becomes T is equals. We have P of what? A intersection E. The sign here is plus. Plus. P of B intersection E. The sign here is minus. Minus. P of A intersection B intersection E. Because this time around we are talking about three sets. Then all over P of E. P of E. That's what we have. What are we going to do further? It is simple. Whenever you have one thing dividing so many things in numerator, they can be divided separately. And dividing them separately, what we have becomes P of A intersection E all over P of E. The sign here is plus. Plus. Here am I. P of B intersection E all over what? P of E. The sign here is minus. I come here. P of what? A intersection B intersection E all over P of what? Of E. I will recall for us that earlier we had said that the probability of an intersection of two events all over the probability of the event that happened earlier is what we call conditional probability. So this P of A intersection E all over P of E can be written as the conditional probability of event A given B. And you and I know that how to write that thing is this way. How to write that thing is, we have that this is written as, okay, you permit me to clean the question. Permit me to clean the question. So this particular place, what we have here becomes what? P of A given E. That is probability of event A occurring given that E earlier had occurred. The sign here is plus. Here are we. The probability of a B intersection E all over P of E is the conditional probability of what? B occurring given that E earlier had occurred. So here is P of what? B given E. The sign here is what? Is minus. Here are we. Then the probability of A intersection B intersection E all over P of E is just like you are saying probability of A intersection B occurring given that E earlier had occurred. And you are going to write as what? P of what? A intersection what? B given that E earlier had occurred. And that is exactly what you were asked to show. You were asked to show that this quantity can be equal to this quantity. And if you watch, look at what I have here. Look at what I have here. So, intersection. Okay, here is to show that this is giving E. Intersection B giving E. Intersection what? B giving E. This is what we are asked to show. Okay? To show that that is equal to that. So, and from what we have on the board, of course, we can see that this is, of course, equal to this quantity. You understand? So, we are going to go over to the third axiom or property of the conditional probability. But before we go over there, of course, let us explain more about this. That you are told that There is a sample space, and in that sample space, there are two events A and B, and there is another event E, such that P of E is not 0. And we are told to show that this quantity is equal to this quantity. We first of all express this quantity as a conditional probability because of this given, the way it is. We remember the property of what of a set, telling us that probability of A union B intersection what E can be written as probability of A intersection what E union probability of what of B intersection what E. Okay, and I think the best way of even writing this in, okay, I also put something like this. Then we are now going to express this one now this way using the property of addition property that says P of A union B is equal to P of A plus P of B minus P of A intersection what B. And then applying it in what we have here now, we are looking at A as if to say it is A intersection E, looking at B as if to say it is B intersection E. And after expressing it, we have this. Dividing it with E parallel, we have this, and this, which equally gave us this one gave us this one, and this one gave us this one. So thank you very much for your audience. Permit me to clean this while we go to the third one. The third one says, and I write, that's the third one. The third one says, and I write. Or number 4. Number 4 says, it said P of A complement given B equals 1 minus P of A given B. Where A complement is complement of A. Is complement of A. That is the one that we are supposed to show now. The probability of A complement given B is given as 1 minus probability of A given B. So we quickly write proof. Let's see how we go about it. Remember that we have that P of S given that B has occurred is given as 1. You know this. That the probability of sample space occurring, given that another set or event B associated with the sample space earlier had occurred, is given as a 1. So this one is clear. Okay. Now, of course, when we are paying attention to A and A complement, you know that when we have what? A union A complement, this is equals sample space. You should know that. When our interest is on A, and you are saying bring together all the elements in A and A complement, they will definitely give you the sample space. So in as much as this thing gives me the sample space, I can equally come here and begin to use it. And of course, you should know that there is no difference like writing this in A complement union what A is equal to S. This and this and this and this are the same thing. And look at S here. So I can easily come here and remove this S and work with this. And the moment I do that, what I will have becomes P of what? Here becomes what? A union A complement given B. This is equal to what? 1. And of course, I know that A and A complement are disjointed sets. They do not have anything in common. And because they do not have anything in common, I can express this thing like this. That this thing becomes P of this my A Look at A here. Given what? B. I'll close it. This my union here becomes plus as usual. So plus. What do I have here? P of A complement given B. Close it. This equals 1. I've expressed this thing to this, knowing full well that this and this are disjointed sets. On trying to make this one solve a formula, this one goes over there, and I'll say, therefore, my P of A complement given what? B is given as, here is what? 1. This one coming over here, minus P of A given B. And that's what we are asked to show. That the probability of A complement given B, A complement given B, is same thing as 1 minus the probability of this. Okay? So this is the third property of this conditional probability. So we are going to take 3 questions with you, solve it well with you, so that when next you see something like that, you'll be able to know how to go about it. So permit me to clean this thing. Okay? So we now take 2 questions to see whether we have understood anything here. Those two questions are, number 1. Number 1 says, and I read, 2 dice are thrown simultaneously, that is together, and the sum of the numbers obtained found to be 7. What is the probability that 3 has appeared at least once? What is the probability that 3 has appeared at least once? So first of all, let us go for the sample space. I will repeat the question. 2 dice are thrown simultaneously, and the sum of numbers obtained is found to be 7. What is the probability that number 3 has appeared at least once? So we go about solving it. We say solution. Solution. Let us use these numbers to represent the faces of the die. I have 1, I have 2, I have 3, I have 4, 5, 6. And I have 1, I have 2, I have 3, I have 4, I have 5, and I have 6. So what is going to occur here is 1, 1, here 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Here is going to be 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 5. 2, this is 6. So here is 3, 1, here is 3, 2, here is 3, 3, here is 3, 4, here is 3, 5, here is 3, 6. So here we have what we call 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. Here is what 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. And here we have what 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. What we mean by 6, this is that we are trying to say that at this particular point, 1 occurs from the first die, 1 occurred here from the second die. Here, 1 occurred from the first die, 2 occurred from the second die down the line. That's what we mean by this 1 comma something. So let us now have our events. Okay? What event we are going to have? Event A is talking about, because they ask us to find the probability that number 3 appeared at least once. So we say let A be event of number 3 appearing at least once. Let event A. So in that case, I have my event A, 3 appearing at least once. Let us check. 3 appeared here. So we are going to pick 3 here. So pick this one, 2, 3. So I have 2, 3. No other place that 3 appeared here. We are here. 3 appeared parallel here, everywhere. So we are going to pick, in fact, 3 appeared here, sorry. So I have 1, 2. 3 appeared here, so I have 1, 3. Close it. No other place where 3 occurred here. 3 appeared here. This is 2, 3. 2, 3. So let us check. No other place here. Let us check here. 3 appeared everywhere here. So I have here, this is 3, 1. This is 3, 2. This is 3, 3. This is 3, 4. This is 3, 5. This is 3, 6. So we are done here. Is there another place where 3 occurred? 3 occurred here equally. 3 occurred here equally. 3 occurred here equally. So I have 4, 3. So I have 4, 3. I have 5, 3. And I have 6, 3. So this is the event of 3 occurring at least once. But the first thing they told me is that the sum of the two numbers obtained is 7. So we are going to use B, event B, to be the event that the sum of two numbers obtained is what? Is 7. So I have B. Then I come here. Let us go and look for a place that can give us 7. I hope you know that 1 plus 6 is 7, 2 plus 5, 7, 3 plus 4, 7, 4 plus 3, 7, 5 plus 2, 7, 6 plus 1, 7. So this line is giving us 7, 7. So I will now pick them. The first one I'm going to pick begin from, I will open. 1, 6 is first one, second one, 2, 5, third one, 3, 4, the other one, 4, 3, the other one, 5, 2, the last one, 6, 1. So this is event B. In this question, what they want us to find, the probability of 3 occurring at least once, given that the sum of two numbers obtained is what? Is 7. If you know that. So what we are going to do, that first of all, let us go and find probability of A. P of A is given as N of A all over N of what? Of S. What is our N of A? How many numbers we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. They are 11. So I have 11 all over. The total of this thing is 36. So I have all over 36. So my P of B, let's count. 1, 2, 3, 4, 5, 6. There are 6 in number. So I have what? This becomes what? 6. N of what? B all over N of S. Which is what? 6 all over 36. Let us now go and look for intersection of A and B. Intersection of A and B. So I have my A. intersection what B is given as. What is it that is found here that is equally found here? Let us check. Everything that is here have to do with 3. Everything here has to do with 3. So let us come here and look for things that have to do for 3 with 3 here. This thing doesn't have to do with 3. Doesn't have to. This one does with 3. This one does with 3. So it's only 2, which means I have that my n of A intersection B is equals what 2, because they are just, let me just say, n of A intersection B is given as, this is a 3, comma what 4. This is 4, comma 3. This 3, comma 4, look at it here, 3, comma 4. This 4, comma 3, look at it here, 4, comma 3. So they share it in common. So for this thing to be this way, it means that therefore my n of what A intersection what B is given as what 2. And if it's given as my 2, my P of A intersection B is given as what 2 all over 36. So for me now to find the probability now, I'm going to say therefore P of A given B equals P of A intersection B all over P of what? B. What is my P of A intersection B? 2 over 36. So this is equals to 2 over 36 divided by. What is P of B? 6 over 36. So I have 6 all over 6, which is equals to 2 over 36 multiplied by 36 all over what? C. This will go, which is the 1 over what? 3. Because this is 1, this is what? 3. So we have 1 over what? 3. In order to manage the size of this class, we are going to draw the curtain for today. The next we are going to do, we also take you into what we call independent events, take you into what we call marginal probability, or what we call independent events, take you into what we call the marginal probability, take you into what we call even the bias theorem and the rest of them. So we have a lot of things that we have marshaled out to discuss with you. Thank you for your audience for today. See you in our next class.